Good morning, everybody. Thank you for joining me today. My name is Ronaldo Pinto. I'm the International Sales Director for AFT. My email is ronaldopinto@aft.com, and I'll be hosting today's webinar. In the previous webinar, we talked about modules XCS and GSC and how to use them. Today, we're going to see some two real cases for each one of these modules. If you have any questions during the presentation, feel free to type your questions in the chat room of the GoToWebinar, and at the end, we'll have a session of questions and answer where I'll be answering your questions. In the agenda today, we're going to see for XCS a case for AFT Fathom validates power plant system conversion, and for GSC, flue gas desulfurization system expansion design optimized. If you want to see more cases of these two, you can go to our webpage, and there's a section in Learning Center that's case study, where you can find any of the cases for each, like you can search for products for like Arrow, or by industry, aerospace, automotive, and select the category, correlation, operation benefits, and sustainability, software features, a model, or applications. You can go hot water. So if you want to see real cases in each one of these, just go to our webpage and you will find the case that will be presented today and other cases that might be of your interest. So let's start talking about XTS module. Let's do a brief introduction of the module. And basically, well, steady state modeling answers many questions, design questions, and that is what AFT Fathom alone is designed for. Some questions cannot be adequately answered without considering how the system behaves over time when submitted to varying operating sequence. Like, is there any undesired process condition during the transient? Does the pump cavitate at any time? How far from the VEP point does the pump operate? Are there any control issues over time? How long does it take to fill a tank? What is the total pump energy consumption over a particular time, varying operating sequence? So AFT Fathom XTS module answers such questions by modeling time transient systems behavior through extended time simulation. XTS module can be described as using a lumped quasi-static state approximation to time simulation. Transient behavior is represented as a sequence of pseudo-static state solution. What XTS does is during a long time period, it takes picture over time, and you determine how frequent these pictures are going to be taken, and then it presents the results. And that's what we're going to be seeing today. So the case we're going to be working with XCS is a real case, and it's AFT Fathom validates power plant system conversion. The company is Sargent & Lundy, and it was done in Chicago, Illinois, USA. This was presented at the Platinum Pipe Award and you can participate in this contest anytime. It's done every year, and you can present any work that you have done with AFT modeling any system. So the description: the project involved converting an existing open loop circuit where water is taken from and discharged to a local river to a closed loop system where the water instead is routed to a new cooling tower. This system provides cooling water to the plant condensers to reject heat and condense the exhaust of the steam turbines. What were the challenges of this project? The plant modification presented many challenges because it integrated new and old equipment. The existing circulating water pumps, intake basin, and concrete tunnels were reused. New equipment included cooling tower pump basin, 4 cooling tower pumps, and 16 cell cooling towers at the cooling tower basin. So here we have the system. The lines in blue are the old system, and the ones in clear gray are the new system. These are the cooling cooling pumps, cooling water pumps. They're existed. This is the new CT pumps, and now we have the new cooling towers that we're going to add. So I'm going to bring the system to talk about what we're simulating here. So as I showed in the previous picture, this part here is the existing. These are new pumps that were added. These are the cooling towers that were added to the system, and it has a new pipe that recirculates the water to the basal in case it's needed. So here we're going to simulate 2 cases. One case, we're going to stop a pump. We're going to trip a pump in the one of the new pumps. So we're going to trip this pump, and the concern is that when we trip this pump, the flow continues going this way, so it can overflow this tank here. So what happens is the system, the control protection system, opens this valve to recirculate the water back to the basal, and also so this is the protection system, and we want to check whether or not it's working. So the first step when you use XTS is you go to analysis and you say time simulation, and you activate it for a transient. So then you have to set the transient events. So here we have 2 transient events. We're tripping this pump, and we're opening this valves to recirculate the water to the old tower. So let's take a look at the trip of the pump. So now we go to transient, and we have a time event that is going to happen. It's going to start in 0 seconds. In 0 seconds, we have the pump functioning totally. In 60 seconds, it's still on. And in 2 seconds, the pump is stopped. Then we have another event here that is a control event to protect the system when this happens. So this, if we go to the transient tab, we have another type of event. It's not a time event anymore, it's a single event, which happens with the condition in the system. The condition in the system is that if pipe 158, the pressure in pipe 158 is greater than 0 psig, it will open the valve to recirculate the water back to the old cooling tower. Now, since we're concerned about the overflow in any of these towers, I'm going to put a design alert. So we have here that the maximum height of the tank, the capacity, would be 31 feet. So I'm going to put a design alert for 30 feet. So to put a design alert, And I'll come here to design alerts and I say design alert manager, and I'm going to create one. Okay, so let me go back here and say cancel, cancel. Okay, so I'm going to create the design alert. So I go to design alert manager. I say create a new one. We're going to give it a name, but we're going to call it cooling tower pump basin overflow. So the design is for the reservoir, liquid height, a maximum of 30 feet. We add it to the list. We update, and we come here and we're going to apply this design alert to the cooling tower basin. So we say okay. So now we have a design alert that is activated for the cooling tower, and anytime that it happens, if there's overflow in the tower, in the cooling tower, we will receive a warning telling us that there's a condition undesired in the process. So we say, okay. So we set the transients. Here we have, as I said, we have two transients. We're tripping one of the pumps. We're opening these valves. And now we're going to go to analysis before we run it. And we go to transient control. In transient control, you'll define for how long you want to simulate. Here, you can simulate minutes, days, years. In this case, we're going to simulate it for 11 minutes, and we're going to take pictures every 2 seconds. So we say okay, and we're ready to run it. So we run it. And now it's calculating all the scenarios for 11 all the cases for 11 minutes, every 2 seconds, taking picture of the steady state. So it's about to finish with 70% over there. Almost done. It's almost 96%. So we go to output. Takes some time because it's loading all the seminars, all the steady state conditions for 2 seconds during 11 minutes. So now the first thing we do is we look at the warnings. There's no warnings here. And another thing that we look at, it's important to see if the control system was activated. We go to event messages, and it tells us that valve Then junction 163 open and at 116 seconds, and the valve in junction 164 open in 110 seconds. So the way XTS presents the results, it has two tabs, transient and the normal. And let's see the tabs for all the elements. So here is the steady state condition. Here you have a sidebar that if I move to the left, it will change the results according to the time I'm looking at. So let's move the bar here. So here we see the results shown here. Okay, give me 1 second. So it shows that the results 76 seconds is the same results for all the junctions, and here are the results for 76 seconds. If I move it to the left, then it will change the time and it will give me the results for each one of them. Let's see. Let's move it. So now we have 128 and 32 seconds. So you can see the results as you move your sidebar and see how they are changing in time. Also, there's another tab where here you see this plus sign. If I hit this plus sign, it will tell me all the results as time passes on. So now we're going to go to the transient for the reservoir, and we go select transient reservoir, and we have here the liquid height level that we want to take care of. So we're concerned of the cooling tower basin, and we want to see how the liquid height changes in time. So I come here and I select and I tell them, give me a quick graph. And it gives me a graph of how the height of the liquid changes in time. As we said, our limit was 30. So now we see that the liquid height only reaches around 28.5, and our limit would be somewhere up here. So we're okay. Another way of looking at this is going to graph results. And here, you will have a transient tab where you can see how it changes in time. So now you select what we want to see. In this case, we want to see reservoirs. So we go to the drop-down menu, we'll go to transient, we go to the drop-down menu, reservoirs, and we want to see the 3 reservoirs to see how the liquid height changes in time. So we tell it to generate. And here we can see the liquid height changing for all the reservoirs. And if there's and as we did, we put a design alert, and we could see that it didn't change in time. Another way to see the XTS results is going to the visual results. And here we're seeing the flow in all of the pipes. So now here you have a sidebar that if you move to your left, it's going to change all the results in here. Let's move the sidebar. So now we have the results for 156 seconds, and I can see them as I move the sidebar to the right and changing time to see how the flow or any variable that you want. To set the variables to see, we all know that it's fathom. We can activate velocity, pressure, and any variable we want to see in the system. So now there's another scenario that was used in this case, and which was cooling water pump trips. So it would be the same procedure. So let's select it. So now the transient is not here anymore. The transient is in these two pumps. So now we're tripping this pumps, and since we're not concerned about the overflow in this one because there's less flow coming back, we're not opening this valve, so the control system wouldn't affect is different for the system. So as we saw, Matt Thomas, engineers of Sanjay Lane, used AFT Fathom and the XTS module featured that were finite open tanks with both constant and variable cross sections, variable speed pumps, a transient event triggered by time, and a transient event triggered by pressure. All the scenarios were run using XTS module to model the long-term transient effects of liquid heights in the cooling tower to see how the non-tripping pumps would react over time to changes in static head. So we saw the results of the graph. This was taken, this was the CT, the cooling tower pump trip, and also the cooling water pump trip. We looked at the graph to make sure that it didn't overflow during the whole operation. So the conclusions of this work, Matt Thomas, senior engineer from Sanjay Lundy, is the software allowed us to determine if and when the basins would overflow or empty during the pump trip scenario. The simulation confirmed that the overflow lines would prevent the cooling tower from overflowing. So you can see that XTS is very useful to model control operation and see how the system behaves, and the control system protect your pipe neck system from any underside condition. So now let's talk about the case of GSC module. But before, let's talk about GSC. What is GSC module? GSC stands for Goal Seeker Control. It automates the process of changing input variables to achieve a design goal seeking. When a single parameter is being changed, the manual process can be done successfully. That could be a case. But when you have when you're varying two or more parameters at the same time, it quickly becomes impractical using manual methods. You can specify groups goals to ensure a group of pipes or junctions satisfies an operating criteria, and you can link variables to force commonality in solutions. GSC module extends Fathom's control modeling capability to include controlling and remotely located variable. For example, calculating a pressure reducing valve set point that controls pressure not at the valve's outlet, but at a downstream location. So the case we'll be analyzing in this case is the flue gas desulfurization system expansion design optimized. The company was Energy Project Catalyst, and the country was Poland. So in this project, it involved designing an expansion of the flue gas desulfurization system at a coal-fired power plant in Poland. Originally, having a capacity equivalent to 4 of the 8 power units of the plant. Increasing environmental regulation required the capacity expansion now to handle all 8 towers. The challenges. The system presented several unique challenges to accurately model its characteristics. The natural draft effect in the discharge stacks provides a noticeable and useful benefit in assisting the system flow that varies as a function of the gas. This is the first challenge to model. Second challenge. The flue gas desulfurization plants have the combined effect of increasing the gas stream temperature and adding mass and volume to the flow by virtue of internal water spray. Another challenge was that an induced draft fan speed control to maintain a controlled furnace exit temperature was simulated, and this is where GSE was used to simulate this. Flue gas conduits in power plants typically have very large cross sections, so the velocity profile is highly irregular, with significant turbulence induced by direction changes, resulting in hydraulic resistance larger than the resistance calculated based on the mean velocity. So here's the plant, and here is where the fans were modeled with curves, the drafts with curves to simulate the draft effect as a function of flow, and accurately simulated. So here we have the new stacks. This is new. These are the 4 plants that were the old ones for the desulfurization system, and this is for the one that are going to be added. Using heat exchanger with a controlled downstream temperature in conjunction with spray discharge junction, this combined effect of the flue gas to streams. So this is for the second challenge. So what they did is they put the spray discharge to add the to subtract the mass and put the heat exchanger. Induced draft fan speed control to maintain a controlled furnace exit temperature was simulated using arrows. So here are the fans that were used. With the multiple ID fans and furnace, this represented 8 variables and 8 goals, automated goals seeking operations, saving significant time compared to manual. So here the variables, this is the pressure that was changed. And the goal was to achieve a minimum pressure of in these sections, in all the air that was supplied here. So let's bring the program here. So this is arrow. As we said, what we want to control here is the pressure in these fans to control, to achieve a supply pressure in the flow that it's in each one of them. So it wants to be done for all these fans in the system. So to do this, first we go to analysis and we activate the GSE. Then we go to the Goal Seeker Control Manager. And we have 2 tabs, goals and variables. In this case, we had a variable for each one of these fans here. What did we want to control? Well, we wanted to control the pressure rise. So in this case, we had J20, which belongs to this J20, and we want to find out the pressure rise to achieve a pressure in the total pressure in the flow supply of 40 psi. So now there's another thing. These two these two fans work together. So here we link them so the solution would be common for both. So these two ones are going to be working in parallel. These two here are coupled in this part here. So now we go to the goals. So here are the goals to be set. So we want a goal of minus 40 Pascal in each one of the flow supply in this case. So here is the assigned variable for each one of them. So in conjunction, we want all these to be achieve a pressure of minus 40 Pascal. So once we set the variables and the goals in the system, we can tell, we say, okay, and we're ready to run the program. So it's calculating pressure. So now we go to output. And in the output, we have three elements that we want to see. Three tabs that initially we want to see. There's two new tabs that it's called Goal Seeker Variables and Goal Seeker Goals. And also there's warning. If he cannot achieve what you're requesting, you'll have a red warning in red telling you that the requested was not requested goals were not achievable by the variables you requested to be changed. So if we see the variables here, now we know the pressure required in each one of the fans, the pressure rise required in each one of the fans to achieve the goals required. And each one of them is minus 40. In reality, we reach 39%, 39.98 Pascal. Then once you see that those are the conditions that are required to achieve the goals you want, you can create a disconnected scenarios with the new variables and the achieved goals. So if I hit here, it will create a scenario and if I go to workspace, wait, let me go to output. So here's this disconnected scenarios, and each one of the fans that in this disconnected scenario, we have a barrel speed set, control set to achieve the, here's the fixed rise pressure that is required to achieve the minus 40 pascals in each one of the flow supply of the system. So conclusions of this work. To solve this task, I needed specialized software which can estimate all necessary flows and pressure in every branch of the system. Moreover, using GSE module, I could set the demand pressure in the furnace chamber. XTS and GSE are very powerful tools and can give you a better knowledge of your system. If you want to try it, just let us know and we can add it to your Fathom license or Arrow license, and you will see the benefits of using it. So now we move on to the sections of questions and answers. Well, there's no questions. Thank you for joining us today. I hope you like the webinar. XTS, as I said, and GSE are very powerful tools. You should consider it, using it for your design. It really saves you a lot of time. Thank you for joining us again. If you have any questions, so what is next? You will receive an email with the link to today's webinar, also informing you of upcoming webinars. You can download for free from our website, or you can request an evaluation license. The price and information in USA are posted in the website, and international, contact your local channel partners. Thank you again for joining us, and hope to see you in the next webinars. Bye.